Hello, good evening. We're continuing our online lecture series on modeling and simulation of earthquakes, soils, and structures. For some reason, I guess I'm not on the screen, that's fine. My name is Jeremic, and with me are Dr. Han Yang and Mr. Heshan Wang, PhD candidate. Dr. Han Yang is actually going today to talk about calculation of modeling and calculation of energy dissipation in structural elements, in this case in beams, in elastoplastic fiber beams. So, Han, please go ahead.
Okay. Thank you.
Oh, I need to
Professor.
allow you to share the screen. Hold on.
Right. Yeah.
Okay, go ahead.
Okay. Share and.
Hold on, something is wrong with the sound. I guess the internet is not very good. Okay, so start from the beginning. Yes, good.
Okay. Can you hear me?
Yes, we can hear you. There was some cutting off previously in the sound.
Oh, okay. Okay. So yeah, today we're gonna continue on the topic of modeling of energy dissipation in earthquake solid structure interaction. So today we're going to talk about the modeling of plastic energy dissipation in structural elements. Specifically, I'll be talking about the beams, but as you will see later, it can actually be also used for other structural elements like wall, as long as they are modeled using the same so-called fiber section technique. I will talk a little bit more on that later. So from the energy balance equation in the dynamic inelastic system. So this is the equation we derived in our previous lecture. So we obtained the total energy balance equation in its global rate form. This one right here, we obtained that from the equation of motion. So here we have all the energy terms that we're gonna need to calculate for a dynamic inelastic system: the kinetic energy, the energy dissipation due to viscous damping, and these three together called material work, and into plastic dissipation, plastic free energy, and the strain energy. So today we're gonna talk about how do we calculate each of these terms for a structural element, specifically a beam element. So we're gonna be using the same thermomechanical framework that we use for our solid materials. So here we have the rate of plastic energy dissipation in this following form. So we say that the plastic dissipation density equals to, this first term is the material work, the stress tensor multiplied with the strain tensor minus strain tensor, which is gives you the elastic strain energy, and then minus the plastic free energy density. And it is very important to realize that this plastic dissipation density should always be non-negative. Now, here are two very important points that we should always be aware of when calculating energy dissipation. So the first one, the stress power that is input into a material body by external loading is transformed into the elastic strain energy, plastic free energy, and dissipation. So all these forms of energy must be considered to maintain a energy balance of the material body. So this principle ensures that the first law of thermodynamics holds. The second point is that the rate of change of plastic energy dissipation should always be non-negative at any given time. In other words, the accumulated plastic dissipation this equation represents the first and second laws of thermodynamics. Okay, so next I'm going to talk a little bit about how do we model the nonlinear structural element in this in our work. So the method we are using is the so-called fiber section technique that was developed by Spokane and his colleagues in excuse me, in 1996. So this fiber section technique essentially just, the idea is to separate a cross-section of a structural element, a beam, into multiple uniaxial fiber materials, including concrete and steel. So this plot illustrates how this idea works. So here you have basically a cantilever beam. One end is completely fixed, and the other end you can have any combination of loading. So here we are looking at the cross-section AA right here. So as you can see, this cross-section is separated into multiple concrete and steel fiber materials. So by combining all this fiber response, you can actually get a pretty realistic response for the structural element, for the beam.
Can I say something? So
yes,
this
please.
is indeed this is the main work that Professor Enrico Spacone did when he was at Berkeley, and then he was a professor at Boulder, and I was a student when he was a professor. So, and then I think he left. He's in Italy now, professor, I think in Pescara. One important note about this type of modeling is that it only works for pure bending. So if you have a beam element that goes through pure bending, that's when you're going to have only normal stresses, no shear stresses. In most cases, you actually do have shear, so the state of stress is a little more complicated than just uniaxial stresses. But this is good enough for some applications, so we use this a lot and mostly for frame structures and so on. It does provide good results, except for some junctions, some connections where one needs to go a little more sophisticated. But in this case, this works good for bending. So let's talk about that. Bending in normal forces, normal axial loading.
Yeah, yes, that is correct. Yeah, it works fine for mainly for moment resisting frames, bendings, and those kind of loading combinations. So, but one important point here we realize that because each fiber potentially can have its own can have a different mechanical response when the beam is loaded. So the energy analysis really has to be done for each individual fiber, and then we can add them together to get the total energy response of the beam elements. So as you can see here, we can have a concrete fiber, we can have steel fiber. So basically we need to develop the energy calculation for each of those material models. So here we will start with the uniaxial steel fiber material. So this material model we're using for the steel was developed by Menegotto and Pinto in 1973 and later extended by Professor Filippo and his colleagues in 1983. So this model can capture the nonlinear hysteretic behavior and isotropic strain hardening effect of the steel rebar material. So this plot illustrates the general mechanical response of this material model. As you can see, the hysteretic behavior and as well as some of the material parameters that are used in this model and also later will be used in our energy calculation. So the main response of the material is defined with these three equations right here. As you can see, the parameters here are the sigma and epsilon are the current stress and strain. So remember that this is a uniaxial material model. So the stress and strain, they are scalars. So the stress and strain here. And then we have the stress and strain at the point of strain reversal, which is the point right there, as you can see when you reverse the loading direction. So the material record at that point. And later, these two variables will serve as material internal variables. And also we have a number of material constants. Here we have the strain hardening ratio and the curvature parameter. So to calculate the energy dissipation and really all the energy parameters for this model, so we will rely a little bit on the graphical approach actually. So here, this is again the same mechanical response of the material. So as you can see, if we are trying to calculate the amount of energy dissipation and the plastic free energy change from a state A here to state B, so assuming we are loading from point A to point B, so this this triangular area, this red area, we assume that to be the amount of energy dissipation during this time step from point A to point B. The detailed justification and derivation of that really assumption can be found in our papers. Later I will provide the details, but here this is what we arrive at. So from point A to point B, like I mentioned before, the plastic dissipation density is this triangular area A, B, and C. Oh, sorry. But we also have the strain energy density. This is the form that we are quite familiar with. Is the same as all the other materials. So we say that the incremental strain energy density equals to the stress multiplied with the actual, this is the incremental elastic strain, because you see this is the incremental stress divided by the elastic modulus. That's the incremental strain. And also we have the plastic free energy density. This expression looks a little bit long, but this is after quite a long derivation. So this is to maintain at the very beginning, if you remember in the thermomechanical framework, the two principles, the first and second laws of thermodynamics. So this is what we finally arrive at, the plastic dissipation density. This is the function right there. And note that all the parameters, the sigma, the epsilon, and the sigma r, this is the reversal point. Those parameters will be recorded with when the material evolves, so you don't need to do any extra extrapolation or calculation. You can just directly use this equation for the plastic energy dissipation density. Next, we move on to the uniaxial concrete fiber material. So this material model we are using here was developed by Yassin in his doctoral dissertation, actually, in 1994. So this model can capture the nonlinear hysteretic behavior and damage effects in concrete. So here, this plot kind of shows the general mechanical response of this material model. First of all, the monotonic behavior of this model is defined using the three equations. As you can see, in the compression side, the response is really divided into three parts. This is when the strain was before the peak strength, and then from the peak strength to the ultimate strength, and then at ultimate strength. So those three equations basically define the monotonic behavior of the model. Here we have some of the the parameters we're going to use for this material. And then for the cyclic behavior of this model, we have a few assumptions. So first, this model assumes that all the reloading lines intersect at a common point. As you can see, this is the unloading path. This is another potential unloading path. This is another one. So all of them are assumed to intersect at a common point, which is defined by this parameter epsilon r and sigma r right there. So this is the equation that you can use to calculate those 2 points. Here we also have the initial tangent stiffness and the constant for just to define the reloading path involved in those expressions. And another important thing that is involved in this model is that the unloading response of the material is bounded by the two limits, the upper limit sigma max and lower limit, the sigma min. So as you can see, those are the expressions. So as you can see, this material model is kind of complicated and is divided into different regions and different paths. So it involved quite a little bit of work to basically define, to develop the energy calculation for this material. Here, what we have are two material internal variables. So those two are the stress and strain at the unloading point on the compressive monotonic envelope. So imagine if you're monotonic loading to here, at this point, the stress and strain are recorded, epsilon m and sigma m, and then you can do a couple of unloading and then reloading. But this is the material variable, kind of record the history of the material, because that record kind of the damage that is this material has experienced. These are the parameters we're also going to use in our energy calculation. So here, to calculate the energy dissipation and all the other energy parameters, we need to come up with a few assumptions or justifications. So here, the first one, we say that the majority of the energy is dissipated during the initial damage in compression or tension. Basically, this is during the monotonic loading branch, the majority of energy dissipation happen. This is consistent with the common understanding that the majority of the damage happens at those points. Now later, when you have cyclic loading, you can also dissipate energy due to friction, due to crushing of those concrete materials, but the majority of energy dissipation should happen during the initial damage.
Can I say something? So essentially, when you
Yes.
start bending and you plastify concrete, or you crack on the other side, or you plastify the steel, and then if you cycle back and forth, most of the damage happens in that first loading cycle. Then everything else is essentially just going to step up. Now, if there's more moment applied, then you're going to essentially have additional first cycle for this additional loading. So then additional damage is going to happen. So, but as long as you cycle within some bounds of moments, the first cycle is going to dissipate most, and then the rest of it just sort of dissipates far less. Yes.
Yes, exactly. Right, and the second point I already mentioned, that in the subsequent cycles of loading, already damaged that it does not dissipate as much as before. We also assume that no energy is dissipated during the unloading path. This is consistent with one of the assumptions used in the model itself. Then the fourth one, we say that when the material is cyclically loaded under compression, energy dissipation only happens when the stress reaches the upper bound. Remember here, I mentioned that the unloading and reloading response of this material is bounded by those two limits. So here we assume that energy dissipation only happens when you hit this upper bound. And last one, no energy is dissipated during cyclic loading when the material is under tension, because we assume when you're under compression, when you have subsequent loading, you can have further crushing and friction. But when this thing is under tension, once it breaks, it shouldn't dissipate further, dissipate any energy.
Once it opens a crack, that crack is there, and then only if you close the crack and then start pushing more, you can plastify. But when you open the crack, that's it for the tension part. Yes.
Yes, exactly. So, yep. So all these points are consistent with our common knowledge of the material, but they are also very important to maintain the first and second laws of thermodynamics I mentioned earlier. So here, again, we're going to use a more graphical approach to illustrate the amount of energy dissipation happens during certain time steps. So here, we say, we can, on the left graph here, we are looking at a monotonic loading step. So here we say for a single loading step from stress state A to stress state B, the amount of energy dissipation is represented by this red shaded area. You can see it's not quite a rectangular. There are some corners. So again, I'm not going to go into details about how this is developed. You can refer to our paper to see the details about this one, but this is the conclusion we arrived at. And similarly for a cyclic loading here, again, we have the same same notation here. From stress state A to stress state B, we assume this is the amount of energy dissipation happened during this time step. As you can see, I zoomed in and I actually stretched the horizontal axis. So if without this stretch, as you can see, this area is actually very, very small compared to the monotonic loading case. This is consistent with what we just mentioned before. So next,
most of the damage actually happens during the first loading into some virgin area, and then after cycling, you might have a little bit of extra, but not much, as you show in this picture. Yes.
Yes, exactly. So next, I'm just gonna give the mathematical expression that I used to calculate those energy terms. So first, again, we have the same strain energy density form. We have the stress multiplied with the incremental elastic strain that gives you the incremental strain energy. Excuse me. And then for the plastic-free energy density, this is the expression we're going to use. As you can see, it's quite long after some derivation. you have multiple other parameters involved, but all of them can be derived directly from the stress state itself or the material internal variables. So they can be directly used explicitly without any iteration or any further derivation. And then here we have the plastic dissipation density. This is the final expression in this red box right there. So yeah, so that was how would I calculate the energy dissipation in a uniaxial steel fiber and concrete fiber. And then if we go back to this picture, so once you are able to calculate the energy dissipation and storage for each individual fiber, you can just simply sum them up for the cross section and then sum them up for the whole beam element.
Yes. Thank you very much.
Yeah, so that,
references, we have references.
Yeah, here are the references. Good. And acknowledgements.
Go back, I'm sorry, go back to references. We're gonna post these slides online. Yeah, this last reference is explaining the theory behind this explanation today. Yes, good.
Right. Yep. I'd like to thank my collaborators, the founding sources, and again, for more information on this and other topics, please go to the Real Easy website. Thank you.
Yes, thank you very much. This is all implemented in Real Easy. So when you run analysis with, let's say, fiber beam or with solids, like we talked about last time, all the output is going to actually have this energy information, so you can actually visualize that and you can use it for some other purposes. Yes. Thank you very much. So, so with this, I will stop recording, and then thank you very much. We'll see you next time when we start talking about other issues in energy dissipation. Thank you.